Okay, welcome everybody. Patrick Gray, robot designer. I thought I would say hi. Today we're going to be talking about the engine that runs the robot. I think of it and call it the engine of the heart. Okay, we're going to be discussing the engine that provides power to the robot, and we'll take a look at that engine. And this is a drawing of the engine inside of this program called SketchUp. And one of the things that we can see when we look at the engine, if we design the engine and show it as though it was completely just made out of metal, which is what the real engine is going to be made out of, there's not a whole lot that you can see. We can also open it in a drawing program that shows what real materials would look like. And when we pop it into place, this is another way of visualizing the engine as though it was made of aluminum. These are the different cylinders of the engine. This is a valve structure here. These are pipes that carry different gases to different locations inside of the engine. And you can see that looking at the engine under this format where it's just metal is not terrifically helpful, other than to know that this is what it's going to look like if it was real, if it was exactly this engine. And I did, as you can see with the design of this engine, it's a kind of a blocky design, and the reason for that is that this type of design is easier to do inside of SketchUp, and it's an experimental engine. It is my guess that if the engine was ever made for real, some of this sharp edges and blockiness of the whole design of it would be taken out of it, but at least that's what it would look like. Another option we have is to a feature of SketchUp where you can modify the materials and change the colors. And so now we can have a version of this engine that is, I think, a lot more comprehensible. We've put labels on the various different structures of the engine, and different structures that have different functions have been given different colors. We can look down inside the engine and see the crankshaft and the connecting rods, and you can see a little bit more clearly how this engine is going to work. We do have the basic principle is the engine will be what is referred to as one way of referring to it is a convention that has a piston connected to a connecting rod, and the connecting rod is connected to an off-axis crankshaft, so that as the piston goes up and down, the crankshaft goes around and around. And we are not actually attempting to get rotary power output from this engine, but the one thing that happens when you take all the different cylinders of the engine and connect the pistons to a single crankshaft is that no matter what speed the engine is rotating at, all of the different cylinders stay in sync with each other, so that wherever any particular cylinder is in its cycle, it is in the correct position in the cycle for what the rest of the cylinders are doing. And that's really what we're using the crankshaft for. And you can see that we have tried to show that we have a geared down angle teeth facing gear system that takes rotation in one axis and turns it into rotation in another axis, and that rotation in that other axis goes up here and rotates around the parts of this valve, and this valve takes gases from one place and sends them to another place, and we're going to describe all of that later. But the first thing we wanted to do was just to discuss the engine a little bit, and our next step here will be to do some general discussions of engines and energy and thermodynamics. Okay, we'll make a recording about issues associated with engines, and this is sort of a overall introductory discussion about engines and energy and power, and so it isn't necessarily needed that we put in any visual activity specific to the engine. So I think I'll just have a slideshow of pictures from the Pistonrobot playing in the background while I talk about this. What we need to understand is that the robot itself is a physical structure. At least once it's built, it will be a physical structure, and in order to have the parts of a physical structure move, you have to put energy into that part that makes the part move. And the reality is the only energy that does this is mechanical energy. So at some point, wherever you are with objects or structures that are moving, where their motion is being caused by energy, somewhere mechanical energy is being created, and then the mechanical energy is applied against the structure to get it to move. And you may have the feeling, well, if it's mechanical energy that we need to do this, why don't we just fill the robot up with mechanical energy and be done with it? But mechanical energy is somewhat complex and difficult to store. Some examples of pure simple mechanical energy being available for the robot, for example, would be to pick the robot up and move it to the top of a hill or a slope and point the robot so it's pointed down the slope. Then the robot would be able to walk down the hill. It would not require any additional energy to do that. Basically, you've given potential mechanical energy to the robot when you picked it up and carried it to the top of the hill. As you let it go down the hill, the robot is using up the potential energy that you gave to it and converting it into mechanical energy for walking. The disadvantage of this is that, of course, the robot can only walk down the hill. In addition, once the robot gets to the bottom of the hill, it can't walk back up the hill. Another example of storing and working with mechanical energy on its own is the example of the mainspring or winding spring of a watch. The crown of the watch is turned. As it turns, it gives mechanical energy to the watch spring. The spring coils itself up and becomes under tension, and the spring has stored mechanical energy in the spring. And then as the spring unwinds itself, it supplies mechanical energy to the parts of the watch, and the watch parts move. The reason that this can work is that the parts of the watch use so little energy that a mechanical spring that you could put in a watch is perfectly reasonable for running the watch. If you wanted a mechanical spring for the robot to do what the activities of the robot are going to be, you would probably need a spring the size of a Chevrolet Suburban and the same weight as a Chevrolet Suburban. The other way that is much more commonly used to hand mechanical energy to an object is to store energy and then have a device that converts stored energy into mechanical energy, and that is really what an engine is. The input side of the engine receives energy and the output side of the engine creates or puts out mechanical energy. There are a variety of different types of storage energy forms that we can talk about, including what I refer to as pixie dust or magic energy. Magic energy is for engines that just run and run and run. You see this in movies and games where there's never any indication of how the robots involved were able to continue to do what they do without any obvious or meaningful source of energy. They never stop and refill their energy tanks. They never plug themselves up. They just run. Now, this is completely okay in the fantasy world because it doesn't make any sense to go through the details of how is the robot building up its or rebuilding up its energy supplies. But in a robot of the real world, we can't use magic or pixie dust energy. Another type of energy that can be discussed is nuclear energy. This is certainly seen because a lot of energy or power can be condensed into a very small size with nuclear energy, but it would involve robots or other objects having nuclear materials inside of them. And in the current world we live in, that's not going to be done because of safety issues and because the robot could be taken apart and the nuclear materials diverted. This really leaves us only two other sources of energy to talk about. One source would be electrical energy. The other is chemical energy. There are many advantages to electrical energy, mostly related to the fact that it's very easy to control. It's well understood. It can be controlled with electronic parts that have no moving parts, which increases reliability. The truth of electrical energy really is it's actually a form of chemical energy in the sense that electricity is put into a battery. The chemicals of the battery move to a higher energy state. When electricity is requested of the battery, these chemicals revert back to a lower energy state and release electricity. The problem with batteries includes that batteries are heavy. They have to be added to the robot. They have exotic materials in them and they're expensive. And it's my guess that for a robot that does what we want it to do, electrical energy is not going to be adequate. Another form of energy we can discuss is chemical energy, and with respect to chemical energy, we are only discussing the use of chemicals in the sense of combustion, where the energy of the chemical is obtained by allowing the chemical to burn with oxygen and generate heat. The heat most of the time is used to generate pressure, and the pressure is the source of mechanical energy. And our engine is going to run under that system. In order for our engine specifications to make any sense, particularly to the argument of why are you bothering with this engine, why don't you just use an engine that already exists, we need to discuss a little bit what is it that this robot's going to do. Most likely it will be financed and constructed by the military because they have a great need for robots and they have the money for the research. What types of military robots can we think about? For example, you could consider a stealth robot, a reconnaissance or sniper robot that would sneak around hidden in a manner where nobody notices it, and it slips up onto whatever the target is and shoots the target and then leaves. Another example would be a heavy weaponry robot that is constructed and reinforced and given enough strength and solidity that it can fire repeatedly fairly heavy kinetic energy weapons that would be too big for regular humans to use. and this would be a firepower robot. The particular robot that we're designing is what we call a walking serviceman robot. This is a robot that walks along with a serviceman who is walking. This is a robot that walks at about 2 to 2.5 miles an hour at a top speed. And this robot can walk all day long. This robot is an autonomous robot. It's extremely important to mention autonomy because there is no power that comes to the robot from the electrical grid. There's no power that comes to the robot from a generator. There's no power that comes to the robot from an infusion of gas or fuel or pressurized fluid connected to the robot. It's completely autonomous. It fills itself up with fuel, and it has enough fuel in it to be able to walk all day long. This is the walking serviceman robot. And as we go through the engine of the walking serviceman robot, we have to be sure to specify what is it about this engine that we consider to be important. It is as we list out the specifications of this engine that it becomes clear that many types of engines that are available will not work for this robot. This is a walking serviceman robot. It's essential that this robot is quiet. It needs to make no noise at all. Therefore, the engine cannot be an engine like a lawnmower engine or a motorcycle engine or a diesel engine. It cannot make any sound. The principle of operation of this engine as we've designed it is that we feel the sound that comes from an engine has two parts. The sound of the parts of the engine themselves moving, which is not a very large sound in an engine where the crankshaft is rotating slowly. The other sound source from the engine is the moving of the gases from inside of the cylinder to outside of the cylinder. The exhaust gases need to leave the cylinder, and the faster the exhaust gases leave the cylinder, the more pressure is required on them to get this to happen, and the differential pressure between the exhaust gas pressure and the surrounding atmosphere pressure is, by definition, the definition of loudness. So the faster the engine runs, the louder it will be with respect to its exhaust gases. Because of this, we want the engine to run very slowly. We want the RPMs of this engine to be in a range of 1 RPM to 160 RPM. That's it. That's all it does. Our design objective, our design thought on this engine is that we will have a large cylinder going slowly so that we will have a quiet engine. We will be burning diesel fuel, and we want to be sure that we don't have a detonation or rapid burn event that would cause a noise. And so the diesel fuel will be injected into the combustion cylinder through a nozzle, and the nozzle will be heated up to 1,000 degrees so that the fuel is at 1,000 degrees when it enters the combustion chamber. The effect of this is that there will be no rapid combustion of the fuel or explosion of the fuel because it will be on fire immediately as it enters the chamber. The principle of operation of the cylinder is an isobaric volume expansion. We add heat to the gas heats up, the pressure heats up, the pressure pushes the piston down, the pressure inside the cylinder actually stays the same. And the work that's derived is from the piston moving down under the influence of the pressure of the heated gases. The crankshaft transmits the power to a water pump that generates the water under pressure, which is used by the piston robot to run the pistons of the robot. The engine has a supercharger that allows use and trapping of exhaust gas heat and exhaust gas pressure so that the efficiency of the engine is increased. The operating parameters of the engine are designed so that the engine runs slowly and makes no sound, and we are attempting to do a type of diesel supercharging so that the efficiency of the engine is increased. Mostly we are doing this in order to have an output of the engine that is equal to pressurized fluid, because what we want for the piston robot is pressurized fluid. We don't need rotational torque energy on the crankshaft. The other objective is to have an engine that is very quiet, actually an engine that can run lower and slower and slower, so that if the Pistonrobot walking serviceman model is not being asked to do very much, then its engine will slow down and slow down and slow down, because this will allow conservation of fuel. But if the Pistonrobot needs to begin doing motion or work, then the engine can bring itself up to a higher speed. With these general considerations done, we will now begin by going back to specific images of the engine, and we will discuss how we are going to achieve these results.